Okay, so as the name would imply, okay, a velocity versus time graph is showing me the object's velocity at various points in time. Okay, just like the position time graph showed me the position of the object at various points in time. Right? On this velocity versus time graph here on the right, what am I seeing? What is that object doing? Okay, remember, it's showing me the object's velocity over time. It's moving at a constant velocity. Okay? Its velocity is not changing. Right? On a position versus time graph, that's an object standing still because its position isn't changing. But here, okay, the position is changing, but the velocity is constant. Okay? In fact, this graph here on the left is the position versus time graph of this motion. Okay? These two graphs are showing you exactly the same object from different points of view. Okay? Our position versus time graph is a diagonal line, indicating that the position is changing at a constant rate. Okay? Here, we're showing the velocity is constant. Okay? So they're showing exactly the same thing. Now, is there a way for me to confirm that these graphs are of the same thing? Like numerical speed. What could I calculate from my position versus time graph that would be readable from this graph? The slope, yeah. The velocity of the object. On this graph, it says the velocity of this object is about 260 meters per second. Okay, 260 meters per second, which is really fast. Okay, I should be able to calculate that from here. Right? If I use y minus b over x to get m, okay, or final position minus initial position, right? So my final position is 1400. My initial position is 100. And that takes 5 seconds. Okay, so 1300 over 5 is 260 meters per second, which is exactly what my velocity versus time graph is showing me. An object moving at a constant velocity of 260 meters per second. Okay? All right. What if, instead, this graph looked like this? Now what is that graph showing me? Now it's showing acceleration. Okay? Because now it's showing me that the velocity of the object is increasing, or just changing in general. Okay? So it's showing an increasing velocity over time. Okay? Now, back in Science 10, you learned this formula. Okay? You could calculate acceleration by taking final velocity minus initial velocity and dividing by time. Does that look a lot like this formula? Okay, it does. Well, there's a reason for that. Okay? It's the same calculation, but it's from this graph instead. Okay? It's a slope calculation. Y minus b over x. It's just this time on the y-axis I've got velocity instead of position. Okay? So when I calculate the slope of this line, I'm calculating the rate of change of velocity, which is acceleration. Okay? Final velocity would be y, 400. Okay? Initial velocity would be b, 100, and that would take 5 seconds. Okay? I'd be able to calculate the rate of acceleration for that object. Okay? Is that making some sense? Yeah? Again, it's not something you need to memorize. You probably memorized it in Science 10 and then forgot it. Okay? That's why we want to teach you the skill of just figuring it out each time, so you don't have to memorize and forget. Memorize and forget. It's an awful cycle, because you usually forget when you need to remember. You don't want that. Okay? All right. What if this graph, sorry, just looking at this graph here, would I be able to calculate the displacement of that object from that graph? Okay. If I gave this question to you in words, you'd probably get it right away. How far does an object go if it moves at 260 meters per second for 5 seconds? How would you do that? Yeah, you'd go speed times time, right? You'd go v equals d over t and manipulate for d. Well, you do the same thing with this. Okay? it's moving at a constant velocity of 260 meters per second, right? So we take average velocity, 260 meters per second, multiply it by the time, and that'll get us the displacement. Okay? In Science 10, you probably memorized this. The area under the line on the velocity versus time graph is the displacement. Does that sound familiar to anybody? Okay. If it doesn't, that's why we don't want you to memorize things. Okay. Here's why that works, though. If you remember that you used to calculate the area under the line, okay? When you calculate this area, you're taking the height of the rectangle, which is average velocity, and you're multiplying it by the base of the rectangle, which is time. And it works even if it's not a rectangle, but it's a triangle. Okay? How do you calculate the area of a triangle? Base times height divided by 2. Okay. With this line, we're saying the object's velocity is changing from 100 to 400 over 5 seconds. Where would its average be? Right in the middle? Okay. Would its average velocity be right smack in the middle of 100 and 400? Is that the height of the triangle divided by 2? That's why that works. Okay? When you calculate the area of a triangle, you go base times height over 2, which is time times average velocity. Okay? That's why that formula worked for you. Okay? You maybe didn't know that before, but now you do. Okay? Now, we're going to work on some of that kind of stuff. Okay, tomorrow with velocity versus time graphs. We're also going to do a fair amount of position versus time graph stuff tomorrow. And then on Thursday, we're going to be looking at doing our first lap. Okay, so I'll be going over that on Thursday.